Hello students, welcome to Inside Physics. Today we are going to discuss about the domain theory of ferromagnetism. See, domain theory was proposed in 1907 by Weiss. He is the scientist who proposed this theory to understand the ferromagnetism in ferromagnetic materials. The magnetism is basically a spontaneous magnetism. So he could able to explain this spontaneous magnetism in ferromagnetic materials based on his domain theory. So what is a domain? It is an area in which the ferromagnetic material is all divided into small regions. So this region contains a net magnetization. The spontaneous net magnetization, which is 100% saturation magnetization, and when it is applied to external magnetic field, each domain, that means a small area inside the magnetic material, is spontaneously magnetized, and the small regions vectorially add up to get the total spontaneous magnetization for a ferromagnetic material. Why he has taken this domain theory? Why we cannot explain normally the spontaneous magnetization of ferromagnetism? Why we need domains? According to Weiss, see, the molecular field developed inside a ferromagnetic material can only be explained when you cut the region into small areas. So you can understand the whole area when you divide it into small regions, it is better. In science, naturally, we do this process in so many theories. So if you understand if you want to understand a particular process, you need to divide that process into small regions or small parts, then you can integrate the total thing to understand the whole process. In the same way, if you understand a ferromagnetic material having a region like this, and the total region inside may be divided into small regions. They may be appearing irregular, but you can imagine that these regions are the cause for total spontaneous magnetization of the ferromagnetic material. So inside these regions you will be having atoms or ions or molecules. So each atom or ion or molecule will have a net magnetic moment, as the electrons inside the atom are circulating in a circular orbits. They will actually develop some net angular momentum and net magnetic momentum because they are moving in circular orbits. That net magnetic momentum of each atom in the domains, when it is not in any external field, the domains will be randomly oriented. So the net magnetic moment will be zero if there is no external magnetic field. So even though the net magnetic moment of each domain is positive, but the total vectorial sum of all the magnetic moments of each domain will be zero in absence of an external magnetic field. So when an external magnetic field is applied, so each domain remains, the space of the region will remain same, but what changes is the orientation of each magnetic dipole. It will be oriented in the direction of the field, so that amounting to net instantaneous magnetic moment. So this is the orientation that has developed within the ferromagnetic material. So when you consider that it in presence of external magnetic field, here no field. So magnetic field is there, here here there is no field. So this is the process which will take place inside the ferromagnetic material when you apply the external magnetic field. So here we can say this is spontaneous magnetization. Spontaneous magnetization is temperature dependent. So how the temperature will affect the instantaneous magnetization means we can say Curie temperature Tc, where this at this temperature the magnetization, spontaneous magnetization will cease once the temperature is increasing with the material. So when the temperature is increasing with the material and that when once the Curie temperature Tc is reached, the spontaneous magnetization ceases. So there will not be further any spontaneous magnetization after Curie temperature. So naturally at absolute temperature, that is 0 Kelvin, the magnetization will be 100%. There is a saturation spontaneous magnetization at absolute 0. So from this temperature, if you keep on increasing the temperature up to Curie temperature Tc, the magnetization will be coming down as the temperature is increasing, and once it reaches Curie temperature, it will be ceasing. Spontaneous magnetization ceases. So after Curie temperature, once you increase the temperature, what happens? The ferromagnetic material will turn into paramagnetic material. So from above temperatures, after Curie temperature, if you coming down cooling the material, while coming to Curie temperature, again the spontaneous magnetization appears at Curie temperature if you are cooling the material from a temperature above Curie temperature. So this is what happens when the spontaneous magnetization happens inside a ferromagnetic material, and it is temperature dependent. So here we will consider what is a domain, ferromagnetic domain. So this domain is a space, already I told you, and these domains are an imaginary space inside a ferromagnetic material. So how the domains will help in establishing the relations between the magnetic susceptibility and applied field and the absolute temperature. We will consider here the Weiss hypothesis as the domain theory of ferromagnetism. So he proposed an internal molecular field. So to understand this spontaneous magnetization, what is internal molecular field? It is a concept proposed by Weiss theory to understand the ferromagnetism. Molecular field. So it is the field developed inside the material because of the interaction of the electrons. Heisenberg told this interaction as a quantum exchange interaction between the electrons. So the internal molecular field. This field is developed only when we apply the external magnetic field. This field is capable of orienting all the magnetic dipoles in the direction of external magnetic field. So internal magnetic field is always represented by Hi. So here H is the external magnetic field, and here what we use the terms when we are going to establish a relation between these internal fields and the magnetization. So here we use M as a magnetization of the material. What is magnetization? We already know this definition. Magnetization M is equal to total net magnetic moment net magnetic moment total net magnetic moment by volume. This is the magnetization, and we all know the susceptibility of a material. Susceptibility is the degree of orientation of the magnetic dipoles that will be orienting in the direction of magnetic field. And here we introduce gamma, a constant which is called a molecular field constant or Wies constant. So we will establish a relation between these values, so that here the internal field Hi can be written as H plus gamma m, where H is the external field, gamma m. This gamma m is the tendency of the atmosphere inside the ferromagnetic material, which tends to align the domains in the direction of the magnetic fields. So this can be considered as the environment or tendency inside the material. So where gamma is the Curie constant, m is the magnetization, internal magnetic field, or it is called internal molecular field. Hi is equal to H plus gamma m. So here we know that for a ferromagnetic material, the susceptibility according to Curie-Weiss law is given by psi m is equal to C by T. Right. So for a paramagnetic state of a ferromagnetic material, we can write psi, that is susceptibility. We can write this as m by Hi. So if you observe these susceptibility relations, see where C is Curie constant and T is absolute temperature, Hi internal molecular field, and this is the relations for a ferromagnetic material and for a paramagnetic state of a ferromagnetic material. What is the paramagnetic state of a ferromagnetic material? So when you increase the temperature beyond Curie temperature, the ferromagnetic material will turn into paramagnetic material. So where C is here, C is Curie constant. Its value is 1.3047. Okay. So it's here, this C, the value will come from the formula which we can use mu naught mu b. This is permeability of free space, this is Bohr magneton, and here n g square j plus 1. So these terms, this g is the g factor, it is j is angular momentum quantum number, and where here this Curie constant can be calculated by understanding this relation. Okay. So here Kb is the Boltzmann constant. Why we take Boltzmann constant? This is understood by the Langevin theory of diamagnetism and paramagnetism, where Langevin considered that the electron cloud as an electron gas. So he applied this Boltzmann constant and he proposed the Langevin variable, which is an indicator of relation between the varying temperature and the susceptibility. That Langevin variable also we will see later. So here the Curie constant. So by these relations, what we can write here? So m by Hi is equal to C by T. Hi internal molecular field, C Curie constant, T absolute temperature. So here how I have written this means, when a paramagnetic state of a ferromagnetic material, this is the relation that applies in its condition of this one. Here what is Hi? We can write M Hi is equal to H plus gamma M is equal to C by T. So if we exchange the terms, and we will find what is magnetization. So here magnetization is considered as Hc by T minus gamma C. Magnetization is considered by Hc by T minus gamma C. So this is the magnetization that is proposed from this formula, where gamma C is considered as a temperature here in this value. So we can find out the susceptibility from this relation. Susceptibility, that implies susceptibility psi is always given by C by T minus gamma C. So this can be written as C by T minus theta. So this is considered as the value of the temperature, where T is absolute temperature. So magnetization can be considered from this relation, and the susceptibility is considered here. See, from this relation, this Hc has become, see, psi we have introduced here, and if you observe this relation, we can identify some points. If T is equal to theta, then the spontaneous magnetization, the susceptibility, will be becoming infinity, so that all the dipoles inside a magnetic material, ferromagnetic material, will be showing the 100% saturation magnetization, and the susceptibility will be moving to infinity. The magnetization will also moving to infinity. So in this way, if the temperature is less than or equal to theta, if the temperature is less than or equal to theta, then what happens? So here the magnetization, spontaneous magnetization, is decreasing when less than or equal to theta. So it will be going to saturation at T is equal to theta. In the absence of external field also, there will be a non-vanishing magnetization inside the magnetic material. So this is the relations when we consider ferromagnetism on the basis of domain theory. So when we consider Langevins variable beta, so that beta, according to Langevins theory of diamagnetism and ferromagnetism, this beta is the Langevins variable, which gives the variation of susceptibility based on temperature. This is equal to where mu m is the permeability of the medium. This is gamma m. Gamma is the Weiss constant by kT. So in this way we can understand the relation between magnetization and Langevins variable. So what you can understand from this? Magnetization can be written as, here magnetization is equal to beta kt by mu m gamma. So from this there is a direct linear relationship between magnetization and Langevins variable. So if you plot a graph between the magnetization and the Langevins function of this variable, then we can understand how the magnetization is actually varying with the temperature. Langevins function L of beta, which actually tells about the temperature variation of susceptibility. So if you plot a graph between Langevin function and magnetization, then you will understand what actually happens with the increase of temperature. What is the susceptibility? Susceptibility is directly related to magnetization. So here the magnetization will sharply increase with the Langevin's function when here T less than or equal to theta. Okay, and the magnetization will come slowly coming to a lesser value when theta is equal to theta, where it is called as Curie temperature. Theta is equal to T is equal to theta, that is called Curie temperature. And when T is less than theta, so already we have written less than theta, so we will, here the magnetization will be greater than theta and for when T less than or equal to theta, the magnetization will be little bit slow. And there is a curve, we can draw a curve like this. Okay, see the curve, and we have three variations when the temperature is greater than theta, equal to Curie temperature, and less than theta. So that that curve drawn between the magnetization and Langevin function corresponds to named as Langevin's curve. Okay, so here this is the picture of ferromagnetism based on Weis theory. The Langevins theory was proposed before Weis theory. Weis developed on the hypothesis of Langevins theory, so he further contributed to this famous ferromagnetic domain theory, and he proposed the domain concept to understand the spontaneous magnetization in a better way. Okay, so this is all for this session. We will continue with some more topics later.